Welcome back, Physics 30. So this is the FM2.6 weight, the force of gravity, and the normal force section. So here we'll look at distinguishing between force of gravity and the normal force of an object, and also calculate the force of gravity as well as the normal force on an object. So weight, first of all, if we look at what weight is really the force exerted on an object by gravity. So your weight varies whether you're on Earth or on the moon or somewhere else. It's the amount of force pulling down on an object. And if we talk about close to the surface of the Earth, the force of gravity is nearly constant, and we can describe the weight as Fg equals mg. Now really what this is Newton's second law somewhat tweaked. So F net is equal to ma, and if we're looking at a being represented by little g, which is the acceleration due to gravity, so quite often we have it pointing straight, since it's operating straight towards the center of the Earth, we often use a negative sign there, negative 9.80 meters per second squared. So that is what this is. So equals ma, which in our case becomes mg. All right. So an object at rest must have no net force working on it. So if it's not moving, that means all forces must be balanced out. So the vector sum of all forces must be zero. The force of gravity is still there, but what is the other force that's being reacting on it? So if we have gravity always pulling down, then there must be another force there. The force exerted perpendicular to the surface is called the normal force. So it is exactly large as needed to balance the force from the object. So quite often how we would draw this picture, instead of the old Abe Lincoln bust here, so we would often just draw like the ground or the table, whatever it is we're talking about, and the object usually is represented as a square. And from the center of the object, we show all the forces being operating on it. So we would have, in this case, a force of gravity, Fg, pulling downwards. And if that was the only force there, this thing would be accelerating, right? Because if we have just simply Fg and that's it, it would be accelerating. But since this isn't moving, since it's staying still, we must have an equal and opposite force operating in the opposite way. And we call that the normal force. And in math class, we would do this to show that these two lines are congruent, or in this case, to show that these two force arrows are equal and opposite. So if I was to look at things vertically here, our net force, our overall force that we have operating, there's two forces that are at play here, Fn and Fg. So we have those two forces operating on each other. Now, if over here this thing is not moving, that means the acceleration is zero. So of course that means that F net must be zero as well, because if acceleration is zero, the net force must be zero. So if this, quite often we show it like this, that is going to be zero. So the sum of these two forces must be zero as well. Or if I subtract Fg from each side, quite often we could say that, okay, the normal force is equal to the opposite of Fg. So that is how we tackle the net force and the forces. Of course, we could have horizontal forces as well, but if we're just talking about objects sitting on a table or on the ground, this is how we analyze it. Just vertically, we have a net force, and then figure out what are the forces that are being involved there. So that kind of leads to the, now of course, we could have Fn, the larger the Fg is, the larger the support force, or Fn will be. So it'll always be exerting to ensure that that object is not accelerating. And of course, if the object is too big, then as I say right here, the force becomes too big. Sometimes the table breaks and I cannot make that Fn force happen. And then the object does accelerate downwards. So we'll take a look at a couple of examples here. So example, a friend has given you a special gift, a box that has a mass of 10 kgs with a mystery surprise inside. Ooh. The box is resting on a smooth, frictionless horizontal surface. Draw a free body diagram. So of course what we could do here is just draw the ground or the table or whatever it is, and then we have our object. Usually just draw it in terms of a square or a rectangle. And the two forces we have being exerted, Fg and equal and opposite. And if we said it's perpendicular, because you can see here it is perpendicular to the surface, Fn. And if this thing is just sitting there, Fg and Fn must be equal but opposite direction. So determine the weight of the box and the normal force exerted by the box. So of course the weight is simply the force due to gravity. So the force due to gravity is equal to mass times gravitational acceleration. So we know it's a 10 kilogram box, so its mass is 10 kgs. And I'll keep it as a negative 9.8 here. So that gives me a total of negative 98 newtons. So that is what Fg is. And then again, if just like I pointed up above, if I analyze this situation vertically, F net is equal to, now my two forces are Fg and Fn. So I have those. And since it's not moving, I know that there's no acceleration. And if there's no acceleration, that means my net force is going to be 0 as well. Because if there's no acceleration, then that happens. So overall, it's not moving. So I have my Fg, which is negative 98. And I have my Fn. So to solve for Fn, as we can see here, yes, Fn is equal to positive 98 newtons. So again, equal and opposite to what Fg is, because it needs to support that object. Alright, so on the next page, let's look at some different scenarios here. So let's look at C. Now your friend pushes down on the box. So we're going to have another force enter the picture, and it's pushing downwards. And it's pushing downwards with 40 newtons. Again, determine what the normal force must be to have this box remain on the table. So of course, let's draw this again. So we'll draw our box here. We have our Fg pushing downwards, but we also have a pushing down force. Let's just call it, we can call it whatever we want, just don't call it lonely. I'll call it Fp for pushing force. So we have a pushing force here as well, pointing down, and I'll just draw it to the side there. And as you can see, Fn will no longer be equal to Fg, but it'll have to be equal to a combination of both. Because if we have more force pulling down on this object, the support force is going to have to be that much higher. So vertically, what we have happening here, so our net force, which is really the resultant vector force, and just look at all the forces I got. I got an Fg, I got an Fp, and I have an Fn. Okay? And again, this is not moving, right? So F net equals ma. So if I don't have an acceleration, then I don't have a net force. So let's see, that's going to be 0. My Fg from the previous part, the Fg is never going to change, right? My Fg from calculated earlier is negative 98. Okay? And what else do I have? My pushing force is 40. But of course the pushing force is 40 and it's being exerted downwards. So I kind of mentioned earlier, now we could have labeled this however we want, but we assumed upwards is positive, downwards is negative. So we'll put that as a negative 40. Then of course we're looking for Fn. So let's see here. So this is going to be simplified to negative 98 and a negative 40 plus Fn. So if I combine these two here, that of course gives me negative 138 plus Fn. So then just simply add 138, add 138. So my Fn is going to be equal to plus 138 newtons. I kind of went over my equal sign there, but there we go. So you can see the normal force is going to have to be bigger because I have more force pulling down. I not only have gravity pulling it down, giving the object its weight, but someone's pushing on it too at 40, so it's almost like the weight is increasing. So I have to be able to support that force. All right, I think I'll stop the video there because the 10 minutes has just surpassed, and then we'll come back in the video 2 and we'll look at the rest of the examples. All right, we'll see you again.